So, so before we get into things, our next test is going to be a week and a bit from now. So next Thursday, and the plan is it will be on topics 3, 4, and 5. So be able to confirm all that next Monday. So topic 3 is what we're currently in right now, which is the biology stuff, so the diseases and other things. Topic 4 is hydraulics and hydrology. It's really usually about one lecture. Topic 5 topic 5 is hydraulics and hydrology. Topic 4 is laboratory and field stuff. It's kind of just a mini unit on a few things. So they're all relatively short topics. Topic 3 being the longest. Yeah. Thursday. So Thursday, yeah. Thursday, or sorry. Did I have that day wrong? Wednesday I meant. Let me just check the calendar. So, yeah, yeah, it should say Wednesday. I get my days of the week mixed up, so let me change that right now. Okay, so Wednesday. There we go. Thank you for noticing. Clearly my brain is still not awake yet. Okay, the other thing that is also of an announcement kind of nature is that 1 month from now is World Water Day. So it happens every year. It's a United Nations kind of event, and every year they have a different theme around water and water awareness and all those kind of things. And this year the theme is, what does water mean to you? So what I'm gonna do this year for World Water Day is I would like each of you to answer that question. So what I'll do is, I haven't exactly decided the format yet. This will be a bonus assignment. So you'll get grades added to one of your tests. I haven't figured out how much it's worth or exact format yet, but probably what you're going to do is going to give everyone basically 1 minute, maybe 2, to answer this question. So if you want to do it in just by talking, or if you want to do a video or make a poster or anything you want, really. I haven't decided really much on it yet, but you've got a month to think about it, and I've got a couple of weeks to kind of think about how I want to grade this kind of thing. Sound good? Okay. So at minimum, go check out their website and see what kind of things they have up there. And I think you can actually access previous year's resources. Some years are a little bit more interesting than others. There was one of the more interesting ones. I remember they had a theme around water and agriculture, and it was actually very informative. All right, so this is where we're at with topic 3. Topic 3. So we talked about waterborne diseases, and we talked about analysis of water. So if you remember, we were talking about mostly the big analysis technique is we're looking for something called fecal coliforms. So what does that mean? It means we're looking for bacteria like E. coli and some related species to see if the water has been contaminated by feces. And we would love to test for everything, but it's expensive and laborious, and it's not really necessary. If you have feces in the water, chances are that something is there that's going to make you get sick. And if there's feces in the water, you're going to find fecal coliforms. That's kind of the way it works. So it's a simpler test to just test for the one thing that's likely to be there. Maybe the water is not going to have Giardia. Maybe the water will not have hepatitis A. But if it has feces in it, it's going to have E. coli and its related parents. And so it's kind of a quick test to see, is the water contaminated by feces, and what standard it's at. So the last 3 things, C, D, and E, are kind of just some, I guess, footnotes in terms of we could spend a lot of time on these things, but we're not going to. We're mostly going to spend a few minutes on these things. Let me shut that door, maybe. It's a little bit noisy in the hallway. So undesirable organic products and waste, I guess that should say C. So this is really just talking about how there's a lot of different types of organic and living material that can cause us problems and undesirable things. So you can see the example here is talking about a sulfur bacterium that creates H2S, which in water dissolves and becomes sulfuric acid, and that can lead to pipe corrosion. It's not necessarily a problem you see everywhere, but anytime you have organic living organisms, there's the potential for them to get in there and cause byproducts that are undesirable. This is another example I found. Organisms leaving deposits such as biofilms, and those biofilms are going to have organisms in there that can interact with all sorts of things. So, for example, causing corrosion in pipes and whatnot. So the big one that I want to talk about today is, of course, algae. This is one that pops up all over the place, and it's doing a couple of things. They can cause bad smells, make it undesirable to swim, if that's what you like to do, and they can reduce dissolved oxygen levels, which is very bad for fish, of course. So I was looking for photos of algal blooms, and this one reminded me, I can't remember what summer it was. Breguet Lake, of course, gets a little bit of algae every summer. There was one summer, I can't remember what year it was, probably about 4 years ago, that it was like this. It was nuts. And usually you go in and the algae is kind of just around the, at the edge of the shore, and you wade through, and maybe by the time you get to your knees or waist, the algae is kind of, it's not that far out away from the shore. No, no, I waded in and made it up to my chest and realized I was coated like this dog. And I was not very happy. Actually, this would have been before the fire because they had a little faucet there. I remember rinsing myself off at the faucet, and I don't think they have that anymore. But it was thick. So that was not fun. So what are algae? Algae are not very well defined, other than to say they're microscopic and they're photosynthetic. Sometimes people will say that algae are eukaryotes that are photosynthetic, meaning they have a nucleus. But then that's kind of one of these where the definition comes out where some photosynthetic bacteria are classified as algae. So it's kind of one of those wishy-washy words that I don't really like so much for that reason. It's not well defined. But they're photosynthetic and they're small things, so they're not plants, right? And there's like, I have no idea how many species, probably millions of species, who knows. Some are a bit more common than others, and some are visible to the eye. Like I said, microscopic, kind of as a, depends on really what you're looking at. There's a type that I'm familiar with that I see some summers, and you just put your hand through the water, and they look like specks, little green tiny specks, but they're big enough I can see with my eye. And I remember putting them under a microscope once, and they're looking really fuzzy. And sort of like these ones here, I have an image, but more fuzzy was the species I was looking at. I have no idea which species they were. Question, comment?
Blaine?
Yeah.
There's a fun fact about algae.
Mm-hmm.
Did you know that flamingos eat them?
No,
and that it causes their feathers to, and that's what gives their feathers the pink color, apparently.
Yeah, like that would be obviously maybe not a green algae, but maybe a red algae or an orange algae, because some algae are not green. So maybe that's what is in there. So I want to talk a little bit about some of the problems with algae. Like I said, obviously I don't like swimming in it, and sometimes it can cause some odor and other problems as well. I want to talk about the dissolved oxygen and some of these toxic algae. I think I have a couple more pictures here. So probably no surprise here. Where did algae come from? Well, they're photosynthetic. So as long as we have the ingredients for photosynthesis, which is light and carbon dioxide, that's going to be part of it, right? But a big part of it is algae. If you kind of think of them as a little bit like plants, you can have more of them if they're fertilized. And so this is why you see a lot of, I'm thinking like dish detergents and shampoos, and particularly laundry soaps nowadays. You'll see some of them that they say they're low phosphate or phosphate free, things like that, because there are a lot of detergents and soaps that do have the phosphates and sometimes nitrates in them. These are things that obviously we find in fertilizers for crops as well. And so, you know, we have to be careful we're not polluting because it can cause algae blooms, which I'll talk about some of the problems in a moment. I think I have another picture. Yeah, here's a picture I took. This is Rainy Lake. This is in Ontario. This is a place I usually visit every summer. And, you know, some years, this was 2018. It was a really, really warm summer there, and it was still. And so when we have, you know, a few days in a row where you have that kind of weather, the algae starts to roll in, and so I took this photo. It was quite thick that day. Thankfully, it wasn't too bad where I went swimming, but this was actually near a dock, and you know, the boats were covered, right? So sometimes we talk about this pea soup effect, right? You know, it kind of looks like a thick pea soup, and it's kind of gross. And sometimes, you know, in the news, people will talk about algae, and they're talking about, you may have heard of these red tides. I'm trying to remember where it was a couple of years ago. I think it was somewhere near the Gulf of Mexico. There was a red tide off the coast of Florida, and there were just dead fish all over the place. So some of these algae will suck out the dissolved oxygen, which is bad for the fish. Some of the red algae have toxins in them, which I don't know much about the toxins and what they're doing to the fish. They kill them, and obviously this is a big thing that people don't want to see. So first thing to think about is, you know, what is going on here? How do algae decrease dissolved oxygen? So I kind of have a little flow chart that I want to draw for you. So just going to get my pen here. So if you think about this, I'm going to just do two flow charts. I'm going to have one here that's going to be called a normal food chain. Okay. And okay, my writing is bigger than I suspected. The one on the right, I'll call it unbalanced food chain. And I'm going to try to write a little bit smaller so that it all fits on here. So normal food chain, you can imagine there's always a little bit of phosphorus and nitrogen in the environment, right? And this is going to promote growth of algae and plants. And so the algae and plants, you know, they're going to feed your small organisms through your zooplankton. And that's going to feed your small fish. And probably lead to also bigger fish. Bigger fish and so on. So if there's a good balance, you can end up with a good, good diversity of fish species, and they're going to be healthy and not too much and all that. So unbalanced food chain, I might have to write just a little bit smaller here to make sure I get everything fit in here. We have excess phosphorus and nitrogen. And so this leads to our algal bloom. There's my algal bloom. And so we're going to get some zooplankton, right? Obviously, is going to feed on that, and probably get some fish. But when you get excess overgrowth, you get, let's see here, excess overgrowth. You lead to problems such as your shoreline gets choked, right? So shoreline choked. Weeds. Or you could call these floating masses. Come on. Floating masses of algae. And so what happens here? We've got the pea soup. So pea soup appearance. I'm just trying to fit us all in here. We got our bad odors. And then lastly, the big thing, we've got decay. And decay happens by basically other microorganisms such as bacteria, and they consume dissolved oxygen. So sorry that I had to squeeze all that in the end there. I meant to make a nicer chart for this, but it didn't get around to it. Usually I do this on the board and it looks a lot nicer. But that's the big thing, is the decay is what is consuming the dissolved oxygen. We've got all that degradation going on by aerobic organisms, and they consume vast amounts of dissolved oxygen. So this fertilization of a lake or a swamp or whatever has a name. It's called eutrophication. And so eutrophication, when you hear this term, usually people are referring to human causes of this. But eutrophication is actually a natural process. As a lake or water body is formed, eventually organic matter is going to get in there, right? So you can imagine over, usually hundreds of years or probably thousands of years in some cases, you're going to have dead leaves and algae and all sorts of things get in there. So eventually a lake is going to start getting organic matter, and there's sort of a life cycle of a lake in terms of, it starts off more on the pristine end, and over the centuries or whatnot, it may get a little bit swampier, just depending how much organic matter or whatnot gets in there. Like I said, the word eutrophication, often we're using that referring to human causes of this, where humans are accelerating this process by dumping in fertilizers or other pollutants that are going to over-fertilize the lake and cause these kind of things. So we'll come back to that word eutrophication. I think I have another slide here somewhere coming along here. So often in Alberta, when we're talking about algae, particularly if you visit provincial parks or recreation areas, we're often, when people are talking about algae, they're actually talking about something called blue-green algae, which is actually a bacterium, a cyanobacterium. And this is the one that sometimes overgrows. I can't remember. I took that picture as well. I went to Lac La Biche. I think that was not too long ago, not last year, but more than 2 years ago anyway. And they had the warnings about the blue-green algae. And if you go to Alberta Health Services, there's all sorts of information about this. And they don't really say too much about the biology of it, just the warnings about what could happen to you. And they're just talking about, you have those warm years and they're still, and these bacteria grow up. And some people, when they drink the water, end up with symptoms. And I'm not sure whether this has something to do with allergies or not, why some people seem to get are more sensitive than others. My wife in particular seems to be really sensitive to this. Not really getting sick, but she gets a sore throat. So not really sure what that's all about, because it's never really affected me. But some people are severely affected. You can see some of these symptoms here: headaches, fever, diarrhea, those kind of things. So when they suspect there's lots in the water those years, they put up the signs and try to advise people, please don't drink the water, and just be aware that that the blue-green algae is there, or the cyanobacteria. So it's just another variety that's pretty common, particularly in Alberta. There's a picture of it. This was was this Edmonton Journal? No, this is CBC News. I don't know if they actually said which lake, but somewhere in Fredericton, apparently, they were doing some research, and they believe that this was the cause of the death of 3 dogs one weekend. So it can be serious. Like I said, some individuals seem to be more affected than others. So you may have also heard of, I don't know if anyone here is from Manitoba, Lake Winnipeg. For years, they've been talking about this algal problem. You can see that's a satellite map of Lake Winnipeg one summer, and it's like the whole thing is massively green. Can't remember if I have some information on this slide or not, but one of the things about the prairie provinces is if you've been through there, if you've lived there, you may have noticed how flat the whole thing is. And there's not a lot of places for the water to go. And eventually, much of the water, particularly in Manitoba, eventually flows into Lake Winnipeg. And the soil in the prairies tends to be decently rich in phosphorus and nitrogen. Never mind, we're adding a whole bunch into it because, of course, we have all that farming that's going on in the prairies. And so Lake Winnipeg is unfortunately the victim here of where eventually all those nutrients go into Lake Winnipeg. And I know somebody who used to have a cabin there on Lake Winnipeg, and because he lived in Winnipeg, and so that's what a lot of people do. They have a cabin there. It's a little bit north of the city, and he complained that he was reminiscing the good old days when the lake was more pristine, and he was saying in the last few years when he owned his cabin, it was just like green algae absolutely everywhere. So no easy solutions for this, right? Like I said, if you think about all the farming that goes on and all the all the rivers eventually kind of flow in that general direction, no easy solutions other than trying to get more of the nutrients to get absorbed into the soil and not flow directly into the rivers, and maybe cut that down. So the cottagers don't generally like it. The fishermen do. It's not at the point where it has low dissolved oxygen levels, and actually the fishermen, they've had record sizes of these videos I was watching on YouTube of these fishermen pulling out these massive fish, and they were saying like these are like twice as big as they were 30 years ago apparently. So the commercial fishermen are very happy about it, but most of the other people are not. And you can look it up and you can see, like I said, all sorts of people at these beaches, and their bodies are all green and coated in algae.
Why are the fish getting bigger as a result?
Because there's just more food for them. Yeah, it goes up the food chain. Yeah, so it's a big enough lake that most of the areas don't have low dissolved oxygen levels, and it's just more food. Yeah. So there's that word again, eutrophication, and it's kind of a little diagram showing that this happens from just natural sediments and organic debris getting in there, but also human fertilization. And I think this is actually showing some of the possible sources of human eutrophication. So you can see there's a whole bunch of things there. For example, discharge of sewage, detergents, agricultural runoffs, different types of industries, and etc. So this is a big thing, right? Obviously, if you have a farm, I don't exactly know all the rules and regulations, but if you do have a farm, you're not really allowed to let all of your manure run into the river, right? So sometimes we have to make sure that the runoff is done a certain way, because we can cause lots of ecological problems. People get mad at you when you do those kind of things. So there are all sorts of other organisms out there. I don't really have a complete list, but you can see this is mentioning that some of these other things produce all sorts of smelly and other byproducts that are out there, and good reason why we want our water is pristine. We don't want things to be poisonous or smelly or bad tasting or anything like that. If the water tastes bad, it may not necessarily be a health issue, but people are not going to be happy, and so you're going to have to do something about it, right? Okay, so biochemical oxygen demand. I know you guys covered this a little bit in the lab, so just want to talk about this as well in the lecture. And sometimes you'll see this called biological oxygen demand. So you'll see either terms, but the most common term is the biochemical oxygen demand. So what is this all about? This is basically trying to see how much oxygen is consumed in a water sample over a certain amount of time. And by what? Usually it's by whatever organisms happen to be in there. Most water samples, unless they're pristine or treated, such as tap water, are going to have some bacteria in there. And most of these bacteria are aerobic, meaning that they can consume oxygen. And so this is a measure of how much oxygen is consumed over a certain amount of time. And this is correlated with the amount of organic material present. So you have a heavily polluted sample of water. So picture a sample of water polluted by, let's say, cow manure. There's going to be all sorts of organic matter in there, right, from the cow manure. And the bacteria are going to, you know, when they're breaking it down, they're going to consume lots of oxygen. And so the BOD number will be really high. If you have a pristine water from, let's say, a lake or something like that, it's going to be much lower. And so this is kind of a measure. It's not a direct measure of the organics in there. Again, there's so many possible organic chemicals, we can't measure each one at a time. But it's a quick and dirty, easy test to do. All you need is a dissolved oxygen meter and a little bit of time. And so that's what you guys actually did in the lab. You took a measurement on day 1 and then took a measurement on, you know, however many days later, and then you just do the calculation. You can get these this little picture showing a jar that is dedicated to the process, and this jar is basically just a dissolved oxygen meter and a dedicated jar, and you know, you press start, it takes the reading on day 1, and then it you know, exactly 5 days later it takes the second reading, and it kind of just simplifies the job. So, you know, water treatment plants, for example, have a whole bunch of these jars because they're doing several samples all at the same time. There are other BOD tests that are, you know, maybe at least worth mentioning. Like I said, this is the simplest one. There is another one called the carbonaceous biochemical oxygen demand, which is a slightly different protocol. And I think I've got a slide on this, so I'll come back to that in a minute. So like I said, this is a really common parameter. It's a really easy test to do, and it kind of gives you an idea of, I guess, like I said, how pristine the water is in terms of organic waste, right? And so it's done for all sorts of water samples. I thought I had a nice chart here, and so you can see there's some different types of water samples from different industries. Those numbers are really high, by the way, if you want to compare that to some pristine water and whatnot. I don't know what kind of numbers you guys were getting for your wastewater, but I'm guessing it was probably not more than 100, but I'm not sure. It depends on the sample from year to year. But you get an idea of what these things look like. Pristine lake water, it's pretty much like less than 10. So what did I miss here on this slide? This is just a bit more detail, kind of talking about you know, what's going on in terms of the chemistry, right? So you know, basically you've got respiration, which is converting organics to CO2. But the big thing that we're looking for is the consumption of oxygen, as measured by the oxygen meter, which is something simple to set up in a laboratory. So for some reason, I don't know who decided this, but the 5 days became the standard, and so usually we say BOD 5. There are a few other measures I've seen out there, but it seems that almost everybody's using the 5-day measure. So I don't know who invented that, but that's kind of the thing that's done. So this is the formula for BOD. So you can see it's basically the measure between the 2 different days, and then you've got a multiplier, right? So generally, what happens is you've got a certain amount of water and the final volume where the sample gets a little bit diluted. So we'll do a sample problem here in a second. You can see there's some more of those BOD jars, and so you know, I think there's the standard BOD jar is, I think, 200 milliliters, although in the lab you guys did what, 50 mils, I think you did, because we had those convenient little little tubes, right? And so it was just a lot easier to do it that way. So here is the here's the sample problem, right? So just a matter of punching into the formula. So remember, our formula is this, so BOD equals D1 minus D2 divided by P. Okay, so D1 is day 1, so that's 8.2 ppm, and D2 is the day 5, so that's 6.2 ppm. Okay, so I'm just going to put that in brackets, and I'll put the the units outside of the brackets. And P was the multiplier looking at the volumes. So P was basically, in this case, we have a 10 milliliter sample, and it's a 200 milliliter bottle. So I think that's the way I presented the formula is slightly different than what's done in the lab. I think in the lab, it says multiply D1 minus D2 times the total volume divided by the volume of the sample. But you can see when you manipulate the formula, it's basically the same thing. So I should get, if I have this calculator right, I think I get 40 ppm. Okay, so pretty straightforward on that. You've seen it in the lab already. Should be no surprises there. Like I said, this is kind of a pretty standard parameter looking at wastewater. It gives you an idea of how polluted it is. It's a very cheap and easy test to do, and it doesn't take a lot of chemicals or preparation or anything like that. You just need VO meters, or in many cases, people have the dedicated jars. So what is this BOD? Oh, yeah, go ahead.
Blaine, I have two questions.
Sure.
Okay, so what if there was a situation where it's like not 5 days? Like, what if it's more or less?
You know, that's a good question. I don't really know the answer to that. I think most places who are doing this routine, they have these little jars. And so, let's say you started your test on a Wednesday and didn't want to come in on Sunday. It doesn't really matter. The jar just records the value for you, right? If you're not doing a routine, then, I guess you would write down the number of days. I'm not sure. Like I said, it's kind of a ballpark thing. In this case here, we're getting a 40 ppm. That's not a very polluted sample. And if you let it run a couple extra days, and let's say you get 50 instead, you still have the ballpark, that you sort of have an idea of how polluted it is, right?
Okay.
Yeah. So another question?
Okay, yes. So parts per billion is equal to milligrams per liter, right?
Yes. Yeah.
So what about other things like parts per billion? What does that equal to? Like grams per liter or something?
So I mean, if your BOD is in the parts per billion, the water is pretty good quality, right? It's definitely less than 10. Parts per billion would be, what would that be? Micrograms per liter, I guess, is what parts per billion would be.
Micrograms per liter?
Yeah.
Okay. And then parts per trillion would probably be less than micro.
Yeah, what's less than micro? Is that nano? Yeah. I've never seen anything in that range. Maybe once. Good question.
Okay.
So like I said, the other one that's cited often is the CBOD, and I'm starting to see this a bit more often. And I think at the wastewater treatment plant they actually do both tests now, which is I don't think they used to do both tests. So it says here they add this chemical, so 2-chloro-6-trichloromethylpyridine, and apparently what that does is it inhibits certain chemical reactions, nitrification specifically. Because what they're trying to do is they just want to see reactions that are oxidizing carbon. And so there are some degradation reactions that oxidize other compounds such as ammonia. And so this is apparently a little bit more accurate in terms of trying to estimate the amount of oxygen that is used to consume basically organic carbon-based compounds. So like I said, starting to see this a bit more often. Because I think there's the belief is that it's a little bit more accurate. But in the end, both of these are kind of, I think of them as ballpark kind of ideas, right? In terms of, how polluted is the water? Okay, we're getting in the hundreds, we're getting in the thousands, we're getting in the 40s, those kind of things. It really is very relative. So one more, what about COD? COD is actually chemical oxygen demand. And I was actually hoping to look into seeing if we can incorporate this into the lab this year. Just with the pandemic, wasn't able to get into the lab this spring and play around with this because I've never done this test before. I think this is often using potassium permanganate, and it's the same idea. What you're doing is basically degrading carbon, but rather than using bacteria to do it, you're doing it chemically, and it's a quicker test. But like I said, I didn't have a chance this past spring to figure out the protocols to see if this is something that can be done in our 3-hour lab period kind of thing. But also takes a little bit more prep work and whatnot, and so it's not quite as commonly done as the BOD, because it's just takes a few extra steps. Like I said, not quite as cheap and dirty, but some people do prefer this number as well. Okay, so last part of today, let me see here. I think we should have lots of time left. I want to talk for just 5 minutes about wastewater treatment. So wastewater treatment, by the way, is like topic 10. So we're going to go into this in way more detail. And sometime over the next couple of weeks, I'm hoping to find out whether we can actually do the field trip. I'm kind of waiting for March 1st, because apparently that's when some of the restrictions are going to get lifted, and then I'm going to contact them and see if they're going to be open to it. And the field trip would probably be at the end of March or first week of April kind of thing. But that'd be awesome. We can go. It's a great field trip, and it's really interesting to see how things work, and the people there really enjoy their job. So what is this all about? Basically, I'm just trying to say that much of wastewater treatment is actually biological in origin. The interesting thing when we talk about water treatment is that drinking water treatment is mostly chemical in origin, in that you're using things to coagulate and take out sediments. You're putting in disinfectants such as chlorine, and those kind of things are all chemicals. The wastewater treatment, on the other hand, we're not using a lot of chemicals. We're more or less trying to figure out how to encourage biology to speed things up. So if you think about the wastes that are in our wastewater, we're talking about things going down the sewer. Most of it's water, right? Some of it will be organic debris from our toilet, and all those things are naturally biodegradable. So the whole purpose of wastewater treatment is figuring out how to speed that up before we put it back in the river. And so I'll show you some pictures, give you an idea how it works. This is a bit of a flow chart. You can see at the beginning, the first part of wastewater treatment is just kind of screening out the big stuff. So think about the stuff that is going down the drain. We've got large particles such as toilet paper going through the sewers. It might pick up grit and gravel. There are things that we don't digest very well. And one of the things, I know there's one guy at the wastewater treatment plant says he will never eat corn for this reason. And then all the other little things that could possibly get put down the drain. I know some people have those, what are they called, in the kitchen sink, and you don't want to stick your fingers in there. You know what I'm talking about? The chopping thingy, the grinder, garburator, is that? Yeah. So there's a lot of people that, like my sister-in-law, like, I can't believe this junk she'll put down that sink. She's just like an entire cauliflower, but anyway. So there's lots of things that will get filtered out and settled out kind of in the beginning. So I'm looking at kind of steps 1 and 2. After that, it just involves really adding a lot of oxygen and a little bit of mixing. And so that's all we're doing, just trying to speed up the process, getting those aerobic bacteria, and then there's some anaerobic processes as well that can get mixed in there. There's different ways to do these kind of schemes. And like I said, speed up the process. And of course, as those aerobic bacteria eat things, they will settle out. And so then you have water on the top, and you have sludge full of bacteria that have eaten all the organic matter kind of on the bottom. And you can see I'm looking at step 5 now. The solid matters can get digested and fertilized and turned into fertilizer or compost or get sent to landfills, depending on where you are in the world. Oh yeah, so heating right here. Yeah, so a lot of this, this step here is actually an anaerobic step, and in that anaerobic step, we're actually making methane, and so the methane can actually be used to heat things, right? It can be burned off. So some cases they just burn it off. I think I'm not sure if that's what they do here. But one of the wastewater treatment plants in Edmonton actually uses it they burn the methane and make electricity out of it. That actually helps run the plant. So you can't just let methane go. It's like a really bad, it's much worse than CO2 as a greenhouse gas. So you've got to burn it off at a minimum. So here's some pictures. There's lots of different systems out there. This is a system that is not really used so much in Canada because we have this little thing called winter. But this is a pretty common system used in some places in the world. This is called a trickling filter. And so what they have is just a massive bed of gravel. This is several meters deep, and they spray the wastewater on this. And you can imagine the water is going to trickle through the gravel. And on the gravel, you're going to end up with biofilms full of all sorts of bacteria, protozoa, and the water basically trickles through, and those organisms will eat the organic matter. And as it trickles through and eventually goes through the system, it comes out pretty clean on the other end. So we don't usually use this in Canada because these things freeze, and these apparently smell really bad, as you can only imagine. One of the big systems we use here is just the system here. This is actually from our wastewater treatment plant, and you can see we've got this, the water is going through there, and you can sort of see it's sort of foamy, and that's because they're aerating and adding lots of bubbles and encouraging the aerobic bacteria in there. And it kind of goes through this, kind of goes from chamber to chamber, and like I said, you've got the settling out of these organisms at the bottom. And by the time you get to the final chamber, the water is pretty clean looking, and by many measures actually cleaner than the actual river water. It's really just amazing, just letting the organisms do their thing. The other amazing thing you'll find out from this tour, if you get to go, is that it doesn't really smell there too bad. There's a couple of places it does. The intake area where they do the screening, that's pretty bad. And there's an area where they do some composting, and that can be pretty bad. But most of the other places, you know, if you think about your wastewater, 99% of it is probably just water, right? You know, if you think about all the stuff we're putting down our drains, you know, our showers, our laundry, our dishes, even what you flush down the toilet, a very high percentage of that is just simply water. So anyway, like I said, more on this in topic 10. There's the aerial view there, where number 1 is where the water goes in. And the other cool thing about this tour is you kind of see everything in order, which is nice. You sort of start at the beginning and work your way, and up there at number 7, they hit it with a little bit of UV at the very end to try to kill anything that hasn't been removed, and then it gets discharged to the river. Okay, so let's see here. We got a few minutes left. I'm going to go into the next topic and kind of talk about a few things that are relevant to this week's lab, and maybe some things that we've seen already in the lab and in the course a little bit. So topic 4 is laboratory and field sampling techniques. And I have a lot more experience in labs than field work. I've done some field work, but you know, at this point it's been a long time, and I was a high school summer student at the time, so I can't really speak too authoritatively about these things other than the information I've gathered from others. But I think our hope is at some point, there was at one point, way back before I was involved in the program, there actually used to be a field sampling course in this program, which would be very useful. But just the way the program evolved, they you know, something had to go, and there was a lot of overlap with that course and some of David's courses and so on. We're hoping to somehow incorporate this back in, at least with some of the air and water sampling techniques. But just trying to figure out how to make it happen, you know, in January, right, isn't going to work. So probably, you know, maybe it'll end up being in another course in the fall or something at some point. But so things to talk about anyway. And there are different techniques out there that may depend on, you know, who you work for and what standard you need those samples to be at as well. So first thing I want to talk about is some lab stuff, and some things that we've kind of talked about a little bit already, at least in the lab, is that a lot of equipment has to be calibrated. And so what does calibrating mean? It just means trying to make sure that instrument is reading within a certain type of standard, right? So different types of instruments have different methods of calibrating. So you've had some experience now calibrating pH meters, and what else? You did the conductivity meters as well? Yeah, so usually that's a pretty common technique for these types of meters, is you have some sort of standard that usually is purchased from a chemical supply company, and they're certifying that standard is it's pH 7 within a certain degree of error. And so the instrument is exposed to that standard and told, you know, this is it. This is your baseline where pH 7 is, or pH 10, or pH 4, or whatever. And then, you know, it's going to use its electronics to, basically when it comes to an unknown sample, to give you that reading with a certain amount of confidence. And so different instruments work in different ways in terms of how they're going to do this, and you're getting different amounts of confidence with different instruments and all those kind of things. pH meters are really interesting. I've used many pH meters, and you know, some of them are just better than others in terms of, you know, like I remember there's this one I used to use years ago, and you'd stick the probe into the sample and it would read 6.8, 6.9, 6.7, 6.2, and you're just like, the numbers keep flipping around. And so that usually means either a couple of things. The pH meter itself is ready to go. But in the case of pH meters, often what it is, it's the probe. The probe can dry out, and that's bad. And they really only have a lifespan of maybe a couple of years max before the probes have to be replaced. Newer instruments tend to have better electronics and those kind of things. Some of them try to be really fancy, where they try to, you know, you can like do a graph in the system where you can plug in your computer and all that. And a lot of that stuff isn't really necessary in my mind, unless you're doing massive amounts of data. So why do we calibrate? I think I kind of, you know, we talked about some of these things, right? Big thing is you want to be sure that your numbers are accurate, right? And you know, you want to be able to, you know, somebody said you measured the pH of that thing. How sure are you, right? And so this is the big part of the question. How is it done? Like I said, by checking against a known reference is a pretty common way to do it. And depending on the instrument, that common reference may be a different thing. In the case of the dissolved oxygen meters, the 100% sample is actually referencing it with the atmosphere. And so you don't actually need a sample for that. The 0% oxygen is a super expensive solution that you can buy. So when should you calibrate? So this is the question when you get a job to ask. Because some things will say you need to calibrate every day. Some protocols will say you need to calibrate before every use. Some protocols will say this instrument needs to be calibrated once every 6 months. The manufacturer may have a recommendation, and your employer may have a different standard. So this is the kind of thing like with a pH meter. Usually, like if that pH meter has been calibrated, let's say in the last hour, I'm okay with it. That's, you know, just from personal experience. I would say any pH meter that's been calibrated within an hour is probably okay to use. But if it was calibrated yesterday, then I'm probably going to calibrate it again today. Other instruments, you know, like I said, it's like an annual calibration or something like that. It really just depends on what it is. And often the two things to go by is what the manufacturer says and obviously an employer. Some employers may have a higher standard. Maybe the manufacturer says, you know, calibrate this once every week, whereas the employer might say you calibrate it before every use or something like that. So other things to think about, right? You can see I have some other things, you know, how reliable is the instrument? You know, if you have multiple instruments, you may find that, you know, one of them is more finicky than another. And so maybe that means it's time to replace or get service. And you can see the hidden costs, right? pH buffers are super cheap. So that bottle of like the pH 7 buffer, I think it's like $1, right? Like that's really cheap. The connectivity standards, they're relatively cheap as well. I think they're somewhere like $5 to $10 a bottle. The dissolved oxygen, the zero oxygen solution, I think it's several $100s for one bottle. And once you open that thing, it's no longer any good for like, it's good for like, you know, probably not even a day, I'm not sure. So, you know, these are things that are balanced by the employer and obviously the lab that you're working into, right? So lots of things to consider there. So what I want to talk about, I guess if we don't get through this today, which I'm not going to obviously, it's fine, we'll talk about it Wednesday. But on Thursday, you're going to use an instrument called a spectrophotometer. And I think for lab 3, you use something similar. Did you use that fluoride colorimetry device? Did you guys use that in lab 3?
No.
Yeah, so it's kind of a
No,
similar.
we do lab, I think that's the lab this week.
Yeah, okay. Sometimes in lab 3 I do as a demo, kind of just depends on how busy we are and all those kind of things. But I know this looks really complicated, but the idea behind spectrophotometry, let me see if I have a picture here. I don't have the picture I'm looking for. But here's a picture like of a solution, right? And you probably know that the darker the solution, the more concentrated it is. That's basically spectroscopy, except for our eye can't tell. Like I can't look at that solution and say, okay, that's 1 mole, right? Our eyes are not really good judges of the situation. So spectroscopy is a system where we have an instrument, let's go back to that original picture, where, oops, too far. You have a light, it's going through a sample, and then you have a detector on the other side. And the detector can actually quantitatively read how much light has gone through. And we can correlate that directly with concentrations. So I'm just going to leave that with you today, and we'll come back to this on Wednesday, and then you guys should be in good shape for understanding what you're doing in Thursday's lab. Okay, so thanks for coming out. I will see you guys on Wednesday. And don't forget, we will have a test next week. It'll be on those topics I mentioned, and I'll confirm everything on Monday, exactly what concepts you need to learn for the test next week. Okay, good to see everyone. We'll talk to you later.